Okay, let's unpack this. We are diving deep into a really critical new paper in this whole race for efficient sequence modeling.
It feels like for years we've been wrestling with this one core dilemma.
Right. How do you keep the expressive power of the quadratic transformer, the one that actually wins on benchmarks, but also get the linear time speed we need for, well, everything at scale?
And the fascinating thing is, the theoretical answer, linear attention, it's been around for a while, it has this promise of linear time inference because it can be written as a recurrent network.
With a 2D hidden state, right.
Exactly, a matrix-valued hidden state. But, and this has been the fundamental friction, in practice, these models have just been slower to train than something like flash attention 2.
Even though the raw math, the FLAP count, is lower.
Right. Slower and often less accurate. They just weren't built with modern GPU architecture in mind. They were I/O naive.
So the authors of this gated linear attention paper, the GLA paper, they decided to attack the hardware side of the problem first. It wasn't the algorithm, it was the implementation. So they have two massive contributions that you really have to see as one unified solution. First, they introduced something called flash linear attention.
Which is a fundamentally I/O-aware, hardware-efficient algorithm. It's built for the silicon.
And the second part builds right on top of that foundation. They generalize that efficiency into a much more expressive architecture.
The gated linear attention transformer. And that leap is what finally allows linear attention to close that performance gap that plagued all the earlier, simpler models. It can finally forget things.
And for you, the listener who's following all the benchmarks, the headline claim here is huge. The GLA transformer isn't just competitive, it's hitting parity with what they call Transformer Plus plus AA, which is basically the LLaMA architecture.
And it's outperforming other big subquadratic models. We're talking RetNet and maybe most critically, Mamba.
Especially on training throughput and long-range generalization, this isn't just a small step. It feels like a real strategic push towards a new paradigm.
Okay, so let's start with that enabling technology, flash linear attention. You said existing linear attention was slower than flash attention 2, even with fewer FLOPs. That seems counterintuitive.
It is.
If the total amount of math is lower, why is the wall clock time worse? Especially on, say, normal sequence lengths up to 4,000 tokens.
It completely changes where you look for the bottleneck. It's not compute, it's memory access, I/O.
Moving data around.
Exactly. On modern GPUs, the runtime is dominated by moving data between the slow high bandwidth memory, HBM, and the much faster but tiny shared memory, or SRAM. Old algorithms were just blind to this.
So flash linear attention was designed from the ground up to be I/O aware. What were the core principles they used to fix this?
They focused on three interlocking ideas. First, just pure memory hierarchy optimization. Maximize your use of fast RAM, minimize those costly trips to slow HBM.
Data locale. Yep. Second, and this is so critical for speed, using specialized compute units. They structured all the math, especially the recurrent part, to look like dense matrix multiplications.
Matmols, because of tensor cores.
Precisely. NVIDIA's tensor cores are built for half-precision matmols. The paper says on an A100, that gives you a 16 times throughput advantage.
16 times faster just by structuring your math differently. Wow, okay, so the whole efficiency argument really pivots on hardware compatibility then.
It absolutely does. And the third part is GPU occupancy. When you have long sequences but maybe a smaller batch size, you have to find parallelism somewhere else to keep the GPU fed.
And that means you have to parallelize across the time dimension.
Which is what led them to the chunkwise parallel form.
Yeah.
It's the key technical compromise.
A balance between the slow serial recurrent form and the fast but quadratic parallel form.
It's the essential trade-off for training. You segment the sequence into chunks, the complexity becomes OCD plus LD together, and the crucial part is that this is subquadratic, as long as your sequence length dollars is bigger than your hidden dimension dealer.
So you do the heavy lifting inside each chunk in parallel and then just pass a small summary state between the chunks sequentially.
Exactly. You trade a tiny bit of sequential work to unlock massive parallelism. That's what GPUs want. And they even offer two I/O-aware versions of this.
Right, for different memory constraints.
The first is the non-materialization version. It's all about memory efficiency. It computes the chunks one by one and never stores the big hidden state matrix in slow HBM.
Which is fine if you have a big batch size already giving you parallelism.
Yep. But for massive sequences, you need the materialization version.
Okay.
Here, you do store the chunk-level hidden states in HBM temporarily. And that lets you compute the final output for all chunks in one big parallel step. It uses more memory up front.
But they get around that on the backward pass, right?
They do. It's very clever. They just recompute those states during the backward pass instead of storing them. It's a classic memory versus recompute trade-off, handled perfectly.
And the proof is in the pudding. As a standalone layer, flash linear attention actually beats flash attention too, even on short sequences like 1K.
Which is where quadratic models are supposed to dominate. It's a total validation of their I/O-aware approach.
So making it fast is one thing, but did they make it smart? This brings us to the gated linear attention layer itself. You mentioned that linear attention historically couldn't forget information.
That's right. It just accumulated things. Models like RetNet tried to fix this with a global data-independent decay factor, gamma. But it was the same for every token.
A bit blunt.
Very blunt. The authors knew they needed something fine-grained and data-dependent, like the gates in an LSTM. So they integrate this matrix-valued forget gate, $.
And that gate gets applied element-wise to the hidden state from the last step. So word det, stgo1 plus the new information.
Exactly. That matrix gate lets the model selectively forget or retain different combinations of features stored in that 2D hidden state. It's way more expressive.
But a full-rank matrix gate for every single time step sounds computationally disastrous and just bloated with parameters.
It would be. And this is where they made a really strategic engineering decision. They chose a reduced rank parameterization. GLIze is actually equal to f alpha t math bf.
So a vector outer product with a vector of ones?
Right. And that vector alpha is derived from the input using a small, low-rank linear layer. This is the crucial choice. It keeps the total parameter count for the whole GLA layer at roughly 4 D2R day.
Which is totally comparable to a regular softmax attention layer. So it's expressive, but still efficient.
And this choice is what really defines the rivalry with Mamba. Mamba achieves a full-rank gating matrix, which sounds amazing in theory.
But what's the practical price for that?
Mamba's structure prevents its core recurrence from being written as a standard matrix multiply. And that has two huge technical consequences. One, it can't really use tensor cores effectively.
So it loses that 16x speed up.
It does. And two, it's forced to store its hidden states only in that tiny fast SRAM during the forward pass. And since SRAM is so small, that puts a hard ceiling on the state size dollars they can use.
So GLA made a trade. A tiny bit less theoretical power in the gate for the massive practical gain of tensor core compatibility, and crucially, the ability to support much larger state sizes.
Exactly. The whole design is an argument that hardware awareness has to dictate your architectural choices if you actually want to be efficient.
Okay, so we have a fast, expressive layer, but now you have to train it in parallel. And the paper says when they tried to do that, they ran into this nasty numerical stability problem.
A very nasty problem.
The parallel form needs this computation with KD baby, where B is a matrix of cumulative products of the gate values. Why is that one term so unstable?
Because those gate values, the bays, are all numbers designed to be slightly less than 1. Now imagine a sequence of 20,000 tokens. The cumulative product of all those numbers becomes
infinitesimally small, basically 0.
Right. And then you try to divide by that near 0 number. Floating point errors just explode. Your training goes to NaN.
So the fix is to do the math in log space. You use the difference of the log B terms instead of a division, but that kills your speed up, right? You can't use half-precision matmoles for that. No tensor cores.
This is the central conflict. Stability wants log space, but speed wants tensor cores. Their solution is this secondary level chunking or tiling that you see in Figure 3. It's a brilliant compromise.
So they use a 2-level tiling to isolate the instability. How does that work?
They realized that the interaction between the subchunks, the orange tiles in the diagram, that can still be computed with fast, standard half-precision matmoles. You can use tensor cores for most of the work.
Okay.
Only the math inside each tiny subchunk, the pink tiles, which is the most numerically sensitive part, only that needs the slower, full-precision log space computation.
So you're isolating the one fragile operation that needs the special handling, and you run everything else on the fastest part of the GPU. That must give you a huge wall clock improvement.
It does. It massively reduces the amount of non-half-precision FLOPs.
Oh.
And they pulled off another huge memory win for the backward pass.
Oh, right, the gradients.
Normally, calculating the gradients for these matrix states would mean storing a gigantic tensor of size times D times DDL in HBM. Just huge.
Which would kill your I/O efficiency again.
Completely.
Yeah.
But they derived a closed-form formula for the gradient law Bailin. And with that formula, they don't need to store that massive intermediate tensor at all. It's a huge I/O reduction.
Let's get to the results then. All this work, this convergence of I/O awareness and architectural expressivity, it has to pay off somewhere.
It does. On standard language modeling, GLA Transformer is competitive with the Transformer plus Baseline and the other linear models. But it really shines on recall-intensive tasks.
Which confirms the data-dependent gating is actually working.
Exactly. They tested it on a synthetic task called multi-query associative recall, MQAR, which is designed to stress a model's memory. And they showed that models with matrix-valued hidden states, so GLA, Mamba, and RetNet, did way better than simpler models.
And crucially, how did GLA do against RetNet?
GLA outperformed RetNet, which is pretty direct evidence that its data-dependent gates are superior to RetNet's simple global decay for recall tasks.
Okay, what about on real-world information extraction like the FDA and SWDE benchmarks?
Same story. GLA showed significantly better performance than all the other subquadratic models, and the paper argues this is because of two things working together.
The larger state size and the better gate.
Precisely. The larger recurrent state size, which flash linear attention makes possible, and the fine-grained selection mechanism from the gate.
The length generalization results might be the most compelling part of the whole paper, though. The ability to handle sequences way longer than what you trained on is sort of the holy grail.
And this is the big architectural win. They trained models only on short 2K contexts. And GLA just showed extraordinary extrapolation.
To what kind of length?
On the PG-19 test set, it generalized effectively to sequences longer than 20,000 tokens. On Slim Pajama, it held up to 18,000 tokens.
And how did Mamba do under the same short context training?
A similarly sized Mamba model really struggled to generalize past 4,000 tokens without being explicitly trained on longer sequences first.
Wow. So that confirms GLA's architecture is just fundamentally better at managing long-range dependencies, probably because that larger matrix-valued state can compress the context much more richly.
That seems to be the case.
So finally, let's tie it all back to the original mission, training efficiency. We know flash linear attention is fast. How does the whole GLA transformer stack up against Mamba on throughput?
The results are really clear. GLA has a significantly higher training throughput than a Mamba model of the same size, especially once your sequence length gets past 4096.
And that advantage comes directly from that architectural decision to be compatible with matmults.
It has to, because GLA can leverage tensor cores where the original Mamba implementation couldn't. Its GPU utilization is just better. That means faster wall clock training time, period.
So this feels like a complete story. They solved the hardware problem with flash linear attention, they added expressivity with the gate, and they meticulously engineered around the numerical stability issues.
All while making sure the final structure was tensor core friendly.
Yeah.
The key takeaway really is that synthesis. It's about implementing an expressive, data-dependent gate in a way that is totally I/O aware.
Which lets you use bigger hidden states and the fastest hardware on the chip.
And that seems to be the most promising path right now for pushing these linear time models to compete head-to-head with transformers. This paper really sets a new bar for efficient LLM training.
That brings us to our final provocative thought for you to consider. Given these demonstrated efficiency advantages and the really improved long-context generalization of gated linear attention, how soon might this type of architecture actually surpass the standard transformer in massive pre-training environments where, at the end of the day, training time and cost are the absolute paramount constraints?